Okay, so in the last lecture, we discussed on active and reactive power with the waveforms, taking two examples of a pure reactance connected to pure inductive reactance connected to a source and a pure resistor connected to a source. Now we have to differentiate reactive load and reactive source as well as active load and active source. So we'll move on to the definition of reactive load and reactive source. Reactive source. We have already seen that the reactive power involves the real power that oscillates back and forth between two devices over a transmission line. We have studied the waveform also based on this concept. Consequently, it is impossible to say whether the power originates at one end of the line or the other with respect to reactive power because it's oscillating, it's pulsating. Now it is useful to assume that some devices generate reactive power while others absorb it, or some devices behave like reactive sources and others behave as reactive loads. Let us see this with an example. Let us take the help of an example to um, differentiate between reactive load and reactive source. So a reactor, let's see, a reactor having an inductive reactance of, that means XL, inductive reactance of 4 ohms, 4 ohms, is connected to the terminals of a 120 volt AC generator. So the source is 120 volt AC generator. So it will look like this. I'll draw the circuit. This is 120 volt generator connected to a source which is 4 ohm, which is 4 ohm. So this I am writing as JXL. Okay, now this is 120 volt. This is 120 volt. Now you are asked to find the value of the current in the reactor. How to find the current in the reactor? IL. Let me represent it by IL. Then IL equals E by XL, which is equal to 120 volt divided by 4 ohms, which is equal to 30 amps. Now, if you want to find the power associated with the reactor, slowly we are trying to differentiate the reactive load and reactive source. Okay, so for that we are trying to find the power associated with the reactor. So as the power is associated with the reactor, I am representing it by Q. Q equals E into I, right? Because it's a pure reactor. So even if I just multiply E and I, what I get is in kVAR, right? So EI equals 120 is the voltage into 30 amps is the current. So into 30, which is equal to 3600 VAR, which is equal to 3.6 kVAR. Okay, kVAR. So this is the power associated with the reactive power associated with the reactor. Now this reactive power is absorbed by the reactor, and because of the absorption of the reactive power, the 3.6 kVAR of reactive power, the AC generator must be supplying it. Consequently, the generator is a source of reactive power. It delivers 3.6 kVAR and the reactive power Q flows in the direction from the generator or from the generator to the reactor. So this is the flow of reactive power. This is the supply of reactive power. This supplies the reactive power and this absorbs the reactive power. That is how we differentiate reactive load and reactive source. Now, if we take the corresponding phasor diagram, you get this E as here 120 volt is a magnitude, but the magnitude of current is only 30 amps, and this is IL. This is 90 degree. This is 90 degree. Okay, now IL lags 90 degree behind the voltage E. So this phasor diagram applies to the reactive load and the reactive source, where reactive load is the reactor and the reactive source is the AC generator, as well as the line connecting them. This is the line connecting them. Okay. Now, if we are including a capacitor as well to the circuit, let's see another example. So suppose I am going to add a capacitor having the same reactance 4 ohms. Okay, so I'm drawing like this. I have a generator, the same 120 volt source, but I'm having an inductive reactance here. Then I have a capacitance. So for this capacitor, I am taking it as minus 4J. Okay, this is also 4 ohms. So minus 4J, and I have ICS current here. This current I am taking it as IL. Then IL I have already found out the value. So 1 minute, let me take it. This is 4 J. This is minus 4J. This is 120 volt. This is 120 volt. Okay. Now, how will I find the current in this case? So the current IC drawn by the capacitor here, the current IC drawn by the capacitor is equal to 120 divided by again 4 ohms, which is equal to 30 amps, because the capacitive reactance is also 4 ohms. And we can conclude that the phasor will be just opposite, because the current IC would be leading the voltage by 90 degree. But in the case of reactance, the current IL would be lagging the voltage by 90 degree. So this 120 I am taking as reference here. Then I have two currents. One is IL, which is 30 amps and which lags the voltage by 90 degree, and another current phasor IC, which is leading the same reference voltage by 90 degree. Again, the current is 30 amps here also. Right, 30 amps. Now, if we take the vector sum of IL and IC, what will I get here? The vector sum of IL and IC is 0, right? Because these two currents have the same magnitude. And in that case, we can say that the generator is no longer supplying any power at all to the circuit, because earlier we had an inductive reactance, a pure inductive reactance. So the generator was delivering reactive power, and the inductive reactance was the reactive load there, the reactive power load, and the reactive power source was the generator. Now the net reactive power is the net reactive current is becoming 0. So what about the reactive power? So the current in the reactor has not changed, right? The current in the reactor has not changed. It continues to absorb 30 amps into 120 volt, right? 30 amps into 120 volt, because the current is 30 amps, right? 30 amps into 120 volt is there already in the reactor, right? So that is equal to 3.6 kVAR. But from the phasor diagram, we see that the net sum of these two vectors is becoming 0. So where is this reactive power coming from? It can only come from the capacitor in this case, which acts as a source of reactive power. So the reactive power delivered by the capacitor is equal to the current it carries times the voltage across the terminals. So here for the capacitor also I have some reactive power, but there it acts as a source. In the reactance, the inductive reactance, it has a reactive power, but it is absorbing. So what is happening is the reactive power delivered by the capacitor is equal to the current it carries times the voltage, which is 120 volt into 3 amps, which is equal to 3.6 kVAR. This is delivered. This is delivered by the capacitor. Right, by the capacitor. Now the reactive power delivered by the capacitor is expressed in watts itself, right? Again, watts itself. Then the reactive power Q now flows from where to where? It flows from capacitor to the reactor. So the flow is like this. That's why when we take the generator as such, we conclude that the generator is not supplying any reactive power. Whatever is the requirement in the circuit is compensated from the capacitor. So this is by this we can conclude that a capacitor is source of reactive power, and it acts as a reactive power source whenever it is a part of a sine wave based steady state circuit. Now let us take another step and remove the reactor from the circuit. I am going to remove the reactor from the circuit. So what happens is I have the source, the same source, but I am having only capacitor. I have removed the reactor, the same capacitor. So the 30 amps current is still the same. I am having minus 4J, right? Now this E is, again, this is 120 volt, right? 120 volt. This is my E. Right, then what happens here is the capacitor is now alone, connected to the terminals of the AC generator. It still carries a current of 30 amps. It still carries a current of 30 amps, which leads the voltage E by 90 degree in the phasor diagram. Right. So the capacitor still acts as a source of reactive power, delivering the same reactive power, which is 3.6 kVAR. So where does this power go? Because there is no reactor in the circuit, which was the reactive power sink in our previous circuit. Now the answer is that the capacitor delivers reactive power to the very generator to which it is connected. So in the first case, the reactive power was delivered by the generator to the reactor when we connected a pure reactance to the circuit. Later we added a capacitor, then the capacitor acted as a reactive power source and it delivered reactive power to the reactor. Now we removed the reactor and we have only capacitor in the circuit. Then also the capacitor produces or delivers the same reactive power, and it delivers it to the very the generator source, which is connected to the capacitor. But this concept, it takes it's a bit difficult to digest. Can a passive device like a capacitor possibly produce any power? The answer is that the reactive power really represents energy that swings back and forth without ever doing any useful work. It's just like a pendulum. It swings back and forth. So the capacitor acts as a temporary energy storing device which stores and releases energy, right, repeatedly, accepting energy for brief periods and releasing it again. However, instead of storing magnetic energy as a reactor does, a capacitor stores electrostatic energy. So this is what we have concluded from the concept of reactive power source and reactive power load. How to differentiate reactive power source and reactive power load. Let's take a small break and we'll continue in the next lecture.